The direction of the net force is the direction of acceleration. Okay. So that concludes Newton's second law. And this is a law that we will continue to use throughout the semester. So what I want to do now is that I want to show you where we're going to do now. So what we want to do here is that we want to apply this type of thinking, and this is what I call N2L thinking, to look at two everyday situations. We're going to start off with force-free motion. And what do we know about force-free motion? One of the things that we call this is we call this equilibrium in the old language. I don't think I can get rid of the word equilibrium. And what that means here is that the acceleration is zero. And if the acceleration is zero, I know that the net force must be zero too. Then our second situation that we're going to look at is that we're going to look at forced motion. And when I look at forced motion, they call this non-equilibrium in the old language. And what this tells me here is it tells me this, that in this situation, we are accelerating. We're either speeding up, slowing down, or turning. As a consequence, the net force is not zero. So even though we've talked about this already, there's something special now. What we want to do here is that by knowing the states of motion. So what are the states of motion? Rest, constant velocity, speeding up, slowing down, or turning. By knowing the states of motion, we ask, what are the forces acting like? That's the main point right there. And by doing that, we could then explain numerous examples of everyday situations. So here we go. Case one. How much time do I have? Okay, I got 12 minutes. So now what we're going to do is that we're going to talk about force-free motion, also known as equilibrium. And you'll see why they call it equilibrium as we start to look at these details. Let's be careful. When I say I have force-free motion, that means zero acceleration. What do I mean by zero acceleration? I could either be in a state of rest, and this is what they call static equilibrium, or I could be in a state of constant velocity, and that's what they call dynamic equilibrium. So there are two equilibrium states. If I'm in an equilibrium state, we then know that the net force is equal to zero. What does it mean when F net is equal to zero? That's the question that we're really trying to ask. And here we go. So in the language of Newton's second law, it goes like this. A net force of 0 tells us all forces must be balanced. Must be balanced. What does that mean? So if I look at the net force, here's what it's saying here. So the net force here really says one of two things. We know that there are horizontal forces and there are vertical forces. So it says that all horizontal forces must sum to 0. And if I'm talking about vertical forces, then I say all vertical forces must sum to 0. So what that means here is that when I go and I look at the net force, of course, and I'm only looking at the horizontal stuff, that has to be 0. If I'm looking at only the vertical stuff, this has to be 0 also. So the question is, what does that mean? What that means here is that the forces, let's say to the right, minus the forces to the left, well, those guys have to sum to 0. That the forces up minus the forces down, those guys have to be 0. So then picture-wise, when I say balanced forces, another way of writing this thing tells me this here. It tells me that the forces to the right must equal the forces to the left. That's what I mean by balanced. The forces up must equal the forces down. That's what I mean by balanced. So force-free motion means, okay, I should be more careful about this. Force-free motion means at least two forces must be equal and opposite to each other. That's what balanced is. So let's go look at examples. Okay, let's go look at examples. So I'm going to look at the first situation. The first situation is we're going to start with rest, and then we'll go to the second situation. So let's go look at everyday examples. So the first example I'm going to use is that I'm going to talk about rest, which is the same as static equilibrium. Okay, that's what we're going to be looking at right here. So let's go do this here. So I got to give you a situation where something is at rest. So what I'm going to do here is that suppose you, not your, you are holding a water bottle in your hand. And it's stationary, right? I gotta have a situation of rest. So immediately what I say here is that because it's at rest or static equilibrium, we know that the acceleration is 0. We know that the net force is 0. So immediately this tells me here is that there must be two balanced forces. So our job here is to identify them. So then we identify by drawing force diagrams. So what do I mean by a force diagram? So let's look at the picture. So remember, you are holding a water bottle. So if I try to draw my water bottle, I'm going to go something like this. Here's my water bottle. And of course, the water bottle is filled with water. Now, I'm not really sure how you would draw a hand, but let's say that this is your hand here. And then you have your fingers wrapped around the bottle here, right? So come in with your hand, and then you're grabbing the water bottle with your hand. So here we go. So there must be two forces that must balance each other out. Well, one, there's clearly your hand. So we then say the force of your hand is doing what? It's holding up the water bottle, so it has to push up. But everything that has mass has a weight, and we know that the water bottle has weight. So then there must be the weight. But what do we call the weight? It's the force of gravity. And how do we typically write the force of gravity? We write it as Fg. That's our force diagram. So our force diagram looks like what? Well, it looks exactly, we typically draw just a dot on this thing, and then we say, yep, there's the force of my hand. And then the force of gravity has to be equal and opposite. And so what we do here is that we draw the forces the same size. And you can see that's what I tried to do. I drew the red one, 3 squares. I drew the green one, 3 squares. So net force tells me what? The only way the net force can be 0, if I call that positive and that negative, this means that this is the force of my hand minus the force of gravity. That's the net force of 0. But that's not the way we interpret it. The way we interpret it is we say, hey, the force of the hand must balance the force of gravity. And this is the way we typically write it. There's a balance of forces between the hand and gravity.